So this video is going to be a short introduction to FIR filters, and FIR stands for Finite Impulse Response Filters. So what FIR filters are generally for are for taking some sampled signals. So we've discussed having continuous signals that are then sampled in time, so you have discrete time samples, and applying a filter to them so that you can choose to retain some frequency components of that signal and not other components. For example, on the signal that I've drawn here in blue, you can see there's some kind of long period carrier here and then a little modulation on top of that. And suppose we wanted to filter out that higher frequency modulation and just retain our carrier. So essentially we would like to implement a low pass filter. Well, one way you could imagine doing this is to take the Fourier transform of the signal that you would like to filter, and we'll find that that signal has some spectrum. Now you can imagine multiplying that spectrum by a bandpass that you'd like to implement. In our case, it may be a narrow low-pass filter that includes only low frequency tones and multiplies the rest of the frequency spectrum by 0, essentially to null it out. So if we implement a filter here by multiplying by the function in red, where it goes up to unity on top and is 0 elsewhere, then the result will be just a portion of the original spectrum, the portion that we are interested in. And when we take the inverse Fourier transform of that residual spectrum, we'll recover our filtered signal. So what we've essentially done here is we've taken a fast Fourier transform, a multiply by a filter, and then an inverse fast Fourier transform. And we know by the convolution theorem that multiplying two signals in Fourier domain, which is what we're obviously doing here, is the same thing as performing a convolution. So you can imagine taking the signal that we've sampled, x of t, and convolving that by some function f of t, which represents the Fourier transform of the filter response that we would like. And it turns out an FIR filter is just an efficient way to implement this convolution. So now we're going to try to implement this convolution. So we have if our signal flows in along a line and we process it sample by sample, and I'm going to describe a delay of one sample with a z to the minus 1 here, then a filter that processes 4 samples at once would have, as our signal flows in here from the left, we would have sample 0 show up on the far right because it was the first one to enter along this line. The sample that's delayed one less of that would be the next newest sample, so x1, and then we'd have yet another sample, x2, and then the newest sample that is flown in along this wire would be x3. So these are just a time series of samples coming in along a wire for this signal. And so now we have these samples all available to us at the same time, and we can use these time samples to implement a convolution by first multiplying each sample by some coefficient, which I'll label f0, f1, f2, and f3. Now f0, f1, f2, and f3 are coefficients that multiply each sample of our signal, and they correspond to samples of our filter as seen in time domain. And as we know, a convolution is a multiplication of one signal by another and then integrating that product. And for discretely sampled time signals, an integration over the time domain is very simple. It's just a sum. Then the output of our FIR filter flows out over here to the right out of that sum. So here what we've done is at one small time window here, x0 to x3, we've done for a separation of 0 the multiplication of x times f and then the integration. Now what we have to do with a convolution, however, is we have to slide one function by the other one in order to do the product and integration as a function of the separation between x and f. And fortunately, time does that work for us here. As we let another signal flow in along this wire, all of our samples advance one to the right. So x0 is replaced with x1, x1 is replaced with x2, x2 is replaced with x3, and x3 is replaced with x4. However, if we keep our samples of our filter function f the same, now we generate the same product and sum, that is the product and integral, for a separation of 1. And if we keep letting time samples flow through the upper part of this filter here, we will eventually convolve the full time stream of x with our coefficients f that represent our filter, the Fourier transform of our desired filter response. So this is basically how you would implement an FIR filter on a chip like an FPGA, where you're processing samples in real time, sample by sample. If you were implementing this on a CPU or something like that, what you'd do is just multiply each sample of your signal by the appropriate coefficient and then slide your signal through your buffer by one sample. Now I've drawn these multiplications suggesting that these are single numbers, that sample x1 is multiplied by a number f0. But in practice, for some arbitrary filter function that you might draw here, f of omega, you can't guarantee that your samples of f are actually real valued. They may be complex valued. In which case this multiply is actually a complex multiply, where you have to multiply the samples of your input signal, which themselves may be complex numbers, times some complex number here. A complex multiply is 3 to 4 times as expensive as a straight up real valued multiply. So if you have a real valued signal, it's rather difficult to guarantee that you can implement any given filter with only real valued coefficients. And this is the service that a lot of filter designer tools will provide for you, is to optimize these coefficients for a desired filter shape such that you are using the fewest number of multiplies that you need, essentially trying to use real valued coefficients where possible. In fact, a thing that's even more desirable is if you can pick a filter shape such that some of these coefficients are 0. One example of a way that you might want to do that is if you were implementing a boxcar filter of some shape and of the appropriate width here. When you Fourier transform that, you're going to get a sinc function. And if you choose the width of your filter just right, you can actually make one of those coefficients be unity here at the peak of that sinc function, and 0 every second sample as you go along. And 0 valued coefficients are very easily to implement. You just omit that multiplier altogether. So there are various considerations in optimizing FIR filters to get the most bang for your buck in terms of processing resources for the filter shape that you'd like. The only other thing to be aware of with FIR filters is that you have a finite number of samples here to implement the filter of your dreams. So in this case we have 4 samples with which we can represent f of t. And that actually is going to set some limits on how steep of a filter we can actually implement. So although you may have wanted to make a perfect brick wall filter with a flat pass band and infinitely fast roll-off into a stop band here, in practice, with only a finite number of samples to represent that function in time domain, you'll find that you cannot implement this ideal filter. Instead, you're going to have some roll-off and you're going to have ripple in your passband. And if you want to try to suppress some of these things, you can sometimes trade ripple for the steepness of your passband roll-off and vice versa by applying a windowing function. So you may take an ideal filter that you would like to implement, Fourier transform that to find the coefficients that you'd like, and then you may apply an overall windowing function to that so that you taper it a little bit in order to optimize your filter response a little bit for things like passband ripple and roll-off. And of course, the more samples that you have here in your FIR filter, the sharper a filter you can represent. And these taps in FIR filters are roughly equivalent to poles in a standard analog filter. And the more poles you add to your FIR filter, the sharper filter response you can obtain.